Hello everyone, we are from Group 4. My teammate is Teng Cheng, Benjamin, and Giliang. Today, the topic is 6 degrees of freedom closed-loop grasping arm using reinforcement learning. This is a table of content for our presentation. Then Teng Cheng will introduce the problem statement, motivation of the paper. Then me and Benjamin will discuss the methodology, and Giliang will make a conclusion for us. Then I will pass the presentation to Teng Cheng.
Thank you, Suxiang. My name is Chao Ting Cheng, and I will continue with the next part. Imagine picking up a fragile glass without breaking it or carefully grasping an irregular object like a plush toy. This task seems effortless to us, but for robots, they pose a significant challenge. Teaching robots to perform such action requires advanced perception, planning, and control system. Today, I review a research paper that tackles this problem head-on. The study introduced a novel framework for 6 degrees of freedom closed-loop grasping using deep reinforcement learning, offering solutions to challenges that traditional methods struggle with. This presentation will cover the background, motivation, and problem statement explored in the paper, providing insights into its approach and contribution to robotics. To understand the research, let's first explore the fundamentals of robotic grasping. Grasping is Grasping in robotics involve three key steps. First, perception, where robots identifies an object and its position in the environment. Second, grasp synthesis, which determines how the robot should grip the object. Finally, planning and control, where the robot executes precise movement to carry out the grasp. While traditional systems work well in static and predictable environments, they often fail in dynamics or partially observable settings. A key aspect of robotic grasping is the degree of freedom, or DOF, available to the gripper. In 4 DOF system, the gripper can move in 3 dimensions and rotate along the single axis. This setup works for simple tasks but struggles with complex or irregular objects. By contrast, 6 DOF grasping provides complete control over the gripper's position and orientation, enabling more versatile and precise grasping. However, this flexibility also introduces greater complexity as the robot must search through a much large range of possible grasp configurations. Over the past few years, reinforcement learning, or RL, has emerged as a powerful tool in robotics. RL allows robots to learn optimal behavior from their interactions with the environment rather than relying on explicit programming. This adaptability makes RL particularly suited for tasks like grasping, where traditional methods often fall short. Motivation for this research stems from the limitations of traditional robotic grasping methods and the opportunities offered by RL. Challenges like rigid predefined pipelines. Most traditional methods rely on predefined grasping strategies or large datasets of labeled grabs. While these work well with familiar objects in controlled settings, they fail to generalize to our new or unpredictable situations. Sim to real. Training robots in simulations is cost-effective and safe. However, transferring these trained models to real environments often lead to poor performance due to differences between simulated and real-world conditions. Lastly, we have high data requirements. Many reinforcement learning approaches require extensive real-world training data, which can be expensive and time-consuming to collect. Deep reinforcement learning provides a pathway to overcome these limitations. By combining RL with visual data, robots can learn to adapt strategies directly from raw images, operate effectively in real time, and even dynamic networks. Rely entirely on simulations for training, reducing dependencies on real-world examples. This research focuses on addressing several key changes in robotic grasping. Degrees of freedom. How can robots leverage 6 degree of freedom grasping to adapt its arbitrary object poses and orientations? Dynamic and partially observable environments. How can robots operate effectively in settings where they have incomplete information about their surroundings? Or sim-to-real transfer. How can models trained in simulation maintain high performance when deployed in real-world applications? And lastly, minimal supervision. How can robots achieve reliable grasping without relying on intensive real-world data or human demonstrations? So the specific problem tackled here is that the researchers designed a scenario where the robot is tasked with grasping objects placed on a table. The robot relies on visual input from an eye in hand RGB camera and its internal state sensor. This problem is modeled as a partially observable Markov decision process, or POMDP, where the robot must decide its action based on incomplete observations. The robot's success is evaluated by a binary reward system, either the graph success or it fails. To address these challenges, the researchers developed a vision-based closed-loop framework with the following features: continuous 6 degrees of freedom action synthesis using reinforcement learning, training entirely in simulation with no reliance on real-world grasping examples, autonomous decision-making for actions including when to close the grippers. Now that we have explored the background motivation and problem statement, we can turn our attention to the methodology and experimental results. These sections will provide deeper insights into how the researchers implement their framework and evaluated its performance. Now I'll pass the time to Xiang and Benjamin.
Okay, so thank you, Teng Cheng. Hello, everyone. My name is Benjamin. So today we at Xiang will be discussing on the methodology for this paper. So the algorithm used for this paper is called stochastic latent integrity, or short form called SLAC. Consists of three main components. One is the latent variable model, other is policy, and also the action value function. So the latent variable model learns useful representation for actor and critic due to the fact that the observation is noisy and the environment is partially observable. And the target policy that is used to be optimized by the agent based on the latent variable z at time step t. And the action value function used to estimate the expected sum of future reward with the discount rate of gamma. So the latent variable model was used as the episode was generated by the current policy with action A and based on noisy observation. The observation collected is stored in the replay buffer, which is similar to the experience replay that we learned. So given a history of action and observation in the replay buffer, latent variables are used to model the true state of the environment and estimating the posterior using amortized variational inference, which is a probabilistic method. So the posterior was defined by this probability, and it is similar to the probability of transition from state Z at time step t to another state at time step t plus 1. So given the action A was taken and the observation of succeeding time step encoded by the function, by the deterministic function f. So here is the some terms used in the latent variable model, and the observation, which is an image taken by the sensor, was encoded into a feature representation using CNN, and then a linear mapping using MLP to find the output. And latent prior is represent the prior distribution over initial state, and latent prior next is just the next step for the latent prior state. So given the initial encoded observation, the initial latent posterior approximate the posterior distribution of the initial latent state Z0, and the observation decoder used to reconstruct old asterisks from the current latent state is used to ensure the latent state capture enough information to explain the observation. So here is some training objective, and the term used is the reconstruction loss, reward prediction loss, and also the KL divergence regularization. The reconstruction loss penalizes the mismatch between reconstructed observation and actual observation. And the reward prediction loss ensure the latent state capture the reward relevant information given the succeeding latent state. The KL divergence regularization encourages the posterior Q to stay close with the prior P, keeping the latent space well behaved. So here are just some of those terms that I explained in the previous slide to form the training objective elbow, which is the evidence lower bound for the model M. So next is the actor and critic. The target policy pi generates the distribution over action, which is performed by the actor, and the state action function Q that estimates the Q value using the Q networks implemented as multi-layer perceptron NLP, which is performed by the critic. So the soft actor critic use entropy bonus to encourage exploration and also stabilize the learning of the model. So the Bellman error for the Q function J was illustrated in the equation below, where Q was the estimated Q value using I network and RT plus gamma V ST plus 1 is the target Q value, where R is the immediate reward at time step T and gamma is just the discount, where V bar is the value estimate for state ST plus 1. So two Q network were used to avoid overestimate and provide a stable bootstrap estimate. So one of the problem in preliminary runs was the divergence due to overestimation of Q function. So a regularization term was added, which is known as conservative Q learning, to the loss of the Q networks. So beta is the Bising coefficient that controls the strength of the regularization across all possible action. The first term encourages the Q function to have lower values, thus penalizing large Q values for action that are unlikely to be taken. The second term reward of Q function for the accurate estimates of the expected values under the policy action distribution. So the objective function of the policy network is defined as below, which is the J, and the first term was the bonus entropy weighted by alpha, and the second term was the Q value that tend to be maximized, encourage exploitation by guiding the agent to select action with high expected reward. So for the policy and Q function parameterization, Q are approximated by Q using the latent state Z using MLP. So the true policy are approximated using pi with the encoded observation and also the action taken using MLP. So both MLP use two hidden layers and Q outputs the scalar, which is the value for the state action function, while pi output a stochastic distribution for action. So the action distribution includes the following: a Gaussian component, which is a 6-dimensional isotropic Gaussian, represents 6 degrees of freedom for the robotic arm, which is 6 axis, and a Bernoulli component with discrete binary action, where it is either represent grab or release. So two of the challenges was dual sensor noise due to the noisy environment, and another one is limited exploration capabilities, although using entropy bonus to encourage exploration. So now I will pass it to Xiu Xiang for the next part. Thank you.
Thank you, Benjamin, for his presentation. So now I will continue the methodology. The author stated that binary reward will complicate the learning. It was because the reward will be given until successfully grabbing the object. Thus, the model does not know the success of each grasping. So it only can learn knowledge when it's successfully grasping. Thus, it will require a lot of exploration. Therefore, the authors used bootstrapping to overcome the problem. They fit in only positive with a 85% success rate example into the model. Furthermore, they try to mimic the simulation as a real-world problem. Therefore, they apply randomization on each domain, like the force of position of the robot arm. They also adjust the position and the camera of the grasping arm. Furthermore, they place a different size target on a different position also. Then they also will modify the time step of the Markov decision process and the observation time of each experiment. After that, they also try to add some noise into segmentation and depth of the image. This is a good way to make robots more industrial because they might have some noise on the sensor or the object in the real world. so the simulation can be more mimic to a real-world situation. They add global noise on each domain, and they add boundary noise in segmentation to help the model overcome poorly defined or misaligned object edge. They also adding edge noise to overcome unreliable depth data. Then they use fast segment anything model to segment the image and use SLSC to track the segmentation. They also use it to predict the lantern stack and fed into OSOP decoder. This is the result of the training. The model trained without domain randomization outperformed to this other. This is because the data without randomization is idealized. Thus, it can get the best result. Then, that is a good sign because the model trained with full randomization can get a 91 success rate and not too low than the model without domain randomization. Then, I will pass the presentation to Giliang. Thank you.
Hi friends, I'm Kiliang and thank you Xiang and Benjamin for explaining the methodology. For my part, I'll cover the experimental setup, results, and conclusion of this paper. For the experimental setup, it contains three main parts: simulation and training, lab setup, and evaluation. The training environment simulated grasping using 145 object meshes in NVIDIA Isaac Gym. Initial training started with 1024 episodes using manually labeled grasp position for 7 objects. This seed data was crucial for the algorithm to learn effectively. The model trained using data from 32 parallel environments, storing 64,000 trajectories in a replay buffer. Pre-training lasted about 50,000 iterations before switching to policy sampling. Domain randomization, especially camera-related ones, significantly improved performance, and the CQR regularization parameter, beta of 0.1, ensured a stable convergence. In the real-world setup, the system featured a Panda 3 robotic arm, a 2-finger gripper, and a wrist-mounted Intel RealSense D405 RGB depth camera. 2 local area network computers managed the operation. One ran real-time Linux for robot control, while the other one, equipped with RTX 4080 GPU, executed the reinforcement learning agent. The evaluation tested 26 objects across 4 different sets: previously seen objects, unseen objects, adversarial objects, and challenging objects. Each object went under 10 trials in various different orientations. For challenging objects like plates, bowls, and plush toys, precise 6 degrees of freedom grasping was essential, as traditional grasping strategies didn't work. A trial was marked successful if the objects remained in the gripper after being lifted. Moving on to the results, the system showed strong generalization and adaptability even in zero-shot scenarios, outperforming the prior methods. The framework achieved the success rate of 88.3% for seen objects, 86% for unseen objects, 85% for adversarial objects, and 74.3% for challenging objects. However, challenges including slight position errors and preference for single-sided graphs and occasional object wrestling. Despite this, its ability to recover from errors demonstrated the robustness of closed-loop control. In conclusion, this research significantly enhances the robustness of robotics. The proposed 6 degrees of freedom framework based on reinforcement learning demonstrates exceptional accuracy on unseen and challenging objects, further showcasing its reliability and adaptability. Another key contribution is its reliance on minimal supervision, using only binary rewards and limited scripted example, which further reduces the need for extensive real-world data. This research paves the way for more versatile and efficient robotic systems. And additionally, we identified the limitation of the current end effector. It is bulky and it can restrict sideways grasping angles, so a redesign of the end effector is suggested for improving sideways grasping. And that sums up our presentation. Thank you very much.